We start the last session for today. The first speaker is Andrei Kotov, that will speak about QCD thermal phase transition, scaling windows, and novel order parameter. So,
okay, thank you very much. And I would like to also thank the organizers for organizing this workshop and for giving me the opportunity to present here. I assume that everybody knows what is QCD thermal phase transition. Probably not everyone is familiar about scaling window, but don't worry, I'll explain it a bit later. And there is also some discussion about novel order parameter, which is useful for studying the scaling properties and the scaling window. So let me start with an introduction and remind a couple of things which I'm pretty sure are well known to the major part of the audience. I would like to say to talk about QCD Lagrangian and its symmetries. We all know that QCD Lagrangian has this form, the quark part, and we can, if we take zero mass, we can separate left and right handed left and right handed quarks so that the symmetries we can rotate them independently, and then the symmetry of the Lagrangian in this case is U1 or UN times UN. The first is for the left particles, the second is for the right particles, or equivalently it's SUN cross SUN cross U1 or cross U1. Now the symmetry breaking pattern, which is also known, is the following. The SUN cross SUN is broken by chiral condensate spontaneously to vector SUN. The first one is baryon number, which is conserved, and the last one is anomalously broken XL U1. So if we now take QCD at non-zero temperature, then there is a phase transition, the restoration of the symmetry, and the question which is discussed and which is very interesting and important, and is what is the symmetry which is restored? Is it just the chiral one SUN cross SUN, or is it plus anomalously? And it is important because it is tightly connected to the order of the phase transition and to the corresponding universality class. Now, if on top of this we add non-zero mass, then we have explicit symmetry breaking by mass terms, and the situation becomes even more complicated, and there is a lot of interesting interplay between these parameters which can be studied and discussed. So the question is, one of the main question is, what is the order of the phase transition then if we have non-zero mass, non-zero quark masses, and if we change them? Of course, it was discussed in previous talks. We have heard in the previous session a lot of detailed discussion. There is this famous Columbia plot, the draft of what is the order of the phase transition as the function of quark mass. And of course, one can talk a lot about it and about different parts, but I don't want to talk about the whole plot. I will mainly concentrate on the chiral limit. So I will talk about QCD phase transition at non-zero strange quark mass and non-zero light quark mass, and in particular what happens if we take light quark mass going to zero. So this roughly corresponds to this part of the Columbia plot, and more specifically then I will concentrate about the physical point and what happens if we discuss the chiral limit starting from the physical point. Now let's look at the Columbia plot, and at this axis here. As we already heard before, there are several possibilities, and there are results which indicate different scenarios. Either there is a first order region in the lower left corner at 3 massless flavors, or there is no first order region. If there is a first order region, it can stop here, or it can it probably goes up to the top. So if we rotate and rotate this axis and I put it horizontally, then I'll just sketch all these scenarios. So I don't want to select any of them at the moment. So it can be, as I said, either the first order region through this whole axis, or it can stop at some point, or there might be some, or there might be that the second order region goes through the whole, stays on the whole line. Now, this is what happens if we take light quark mass 0 and we vary strange quark mass. Let's take add to this non-zero light quark mass. And let's, for the time being, assume that we have a first order region for flavors, which then ends at some critical strange mass, and then it goes into second order region, second order line. Then usually it is expected that this second order line is O4 universality class. And if we are sitting in the vicinity of this O4 universality class, then the behavior of corresponding order parameter is usually is given by universal functions, which are determined by this universality class. Of course, there are some non-universal corrections, so this is valid only in some region in the vicinity of this second order line. So, and this is what I call scaling windows. This window where this can be explained to some approximation by these universal functions. Again, here we have, if we assume that we have another Z2 second order line, then there might be some scaling window. In the alternative case, if there is a for example, there is the first order phase transition, it should persist also for non-zero light quark masses, and probably in some critical line, which is shown here by cyan dots. And then there above this line, there might be some scaling window where this universal behavior describes the system. And the question is, let's remember that we have our real world, we have real QCD. What is this physical point where it stays on this plot? Is it somewhere above the scaling window, or is it very, very close, like this? And we can describe the behavior of corresponding functions by the scaling. So it is more or less settled that the transition is not of the first order at the physical point. So I assume that the physical point cannot be below this line here, or cannot be here. Now let's have a closer look at the equation of state. This universal function, which describes the order parameter, in our case, the chiral condensate, as a function of external symmetry breaking field. In our case, it's quark mass. So then the expression for this order parameter is given by this simple formula. And it would be nice that we can if we could somehow suppress these non-universal terms. And in order to do this, let me introduce another parameter, which is simply given by this expression. We take m minus derivative m with respect to h times h, which I call psi bar psi 3. It will become clearly more clear in the following why I call it psi bar psi 3. But what is already clear is that linear contributions in this parameter are absent simply by its construction. So any linear contribution is h is absent. I would like to say that I will mainly concentrate on O4 universality class and present the results of it. Also, I will briefly discuss other possible scenarios, Z2 scaling mean and the mean field behavior. As a byproduct of this study, I will also provide some estimation of the critical temperature in the Chiral limit. And it turns out that it is quite robust about with the predictions of various scenarios. So let's have a look about at this order parameter a bit closer. In our case, if we take chiral condensate, then its derivative with respect to mass is chiral susceptibility, and it's just psi bar psi minus m times susceptibility. Here on the spot, one can see how this order parameter behaves if we assume that it scales according to O4 or mean field universality class. So let's green lines correspond to psi bar psi, blue lines correspond to psi bar psi 3, and purple line correspond to this psi bar psi 3 rescaled. What one can rescaled, I mean that it goes through one point here with chiral condensate. What one can hear from this plot is that this order parameter, it drops down very fast as x increases. So comparing to chiral condensate, it decays with much faster exponent, and it can be predicted again by the equation, by the universal equation of state. As I mentioned, any linear contributions in mass are absent in this combination. In particular, the divergence, the leading divergence, which is proportional to 1 over a squared, is also absent in this contribution, which is very nice for studying. And in the chiral restored phase, it's if we look at the Taylor expansion with them, then it starts from the m to the cube. Let's look at the critical temperature which we extract from this order parameter. We can extract it from the inflection point or from the peak of the corresponding susceptibility. And comparing to the peak in the chiral condensate and to the peak in this new order parameter, you can see that they all scale with the same function. So TC will scale with the same expression given here, but the coefficient in front of pi and mass is different. In one case, it's 0.74 for the chiral condensate. In another case, it's 0.89. So the pseudocritical temperature extracted from this order parameter, according to O4 universality class, should be also closer to the one in the chiral limit. Now let me turn on to some to the results of the latest simulations. Let me say a couple of technical details. The simulations were performed with twisted mass fermions at maximal twist in the fixed scale approach, so that lattice spacing is fixed and the temperature is varied by varying temporal extent. And we have a set of masses starting from the physical up to heavy quark regime. So first, let's look at the critical temperature and how it scales with the pi and mass. Here on this plot, our data correspond to red, blue, and green points, together with the lines which are given by the predictions of by the fits with O4 universality classes and by the corresponding extrapolation. It would be also, of course, interesting to compare with the results of other groups, and it turns out that they are in nice agreement. And we can also make a prediction for the critical temperature in the chiral limit, which in this case would be 134 plus 6 minus 4 MeV, based on the extrapolations of all these three observables. Another interesting approach how this one can estimate the critical temperature in the chiral limit is that if we take this new observable psi bar psi 3 and we rescale it by the quark mass to the appropriate in the appropriate exponent, then it should be constant exactly at the critical temperature in the chiral limit. So that that is exactly what is shown on this plot, and you see that all three curves for the pi mass understudy, they go through one point, and it gives another estimation of this T naught, which is in agreement with the previous one. It's 138 MeV. Up to now, I mainly discussed the feeds to the data with O4 universality class. But let's have a look whether we can describe the data with other behavior. For example, one can try to take mean field exponents and mean field functions, and it turns out that if we take mean field functions, then they are not working very well for the lowest pi mass for 140 MeV, but for a higher pi, in principle, they can try. Alternatively, coming back to O4 universality class, if we perform the feature of the data with O4 universality class, then it works also pretty decent, but the critical temperature extracted from the single feed T naught is completely different from the one that we obtained in previous two approaches. Only for the lowest pi mass, the prediction for this T naught is comparable with the results that I showed on previous two slides. So all in all, let me conclude from this point that for larger pi masses, probably mean field behavior can describe our data, but there is some discrepancy, some tension between O4 universal functions. On contrary, for the lowest pi mass, for the physical one, there is some tension between mean field and the data, and O4 can describe our data pretty good. Alternative scaling is based on Z2 scenario when there is a first order transition in the chiral limit, which persists up to some critical pi mass, and then it turns out into a crossover. I have to say that unfortunately, at the moment, the data cannot distinguish between these two scenarios. So if we fix by hand this critical pi mass to 100 MeV, then the data can be described with reasonable accuracy. So one cannot fully exclude this scenario. But from the good point of view, if we take this critical pi mass equal to 0, then these feeds are not distinguishable from O4 universality. So I would like to say that this prediction, this 134 MeV for the critical temperature in the chiral limit is robust against the different scenarios and different universality classes. Now let's look at the large temperature behavior of this quantity. And here on this plot, I showed this psi bar psi 3 divided by m pi to the 4, or quark mass cubed. The reason why I do it is because that in the symmetric phase, one would expect that its Taylor expansion starts from m to the cube. So the curves should collide onto 1 if this is so. And indeed, if one takes temperatures larger than 300 MeV, all the points collide on one curve nicely. Below 300 MeV, behavior is completely different. And again, if we take the predictions of O4 universality class, then it says that psi bar psi 3 should be proportional to the T in the appropriate exponent. And it turns out that it works pretty well for this Pine mass that we study. So it means that before 300 MeV, O4 predictions works, and above 300 MeV, their simple analytical prediction describes the data. It's kind of interesting that there are a lot of actually indications that quark gluon plasma contains some thresholds. First of all, I would like to mention that there are, if we look at the topological susceptibility, then the first preliminary results also showed that at 300 MeV, there is a change of trends, and it's the onset of dilute instanton gas behavior. There are also works by other groups which observe thresholds in QGP around 300 MeV based on monopole condensations on the Dirac spectrum, some symmetry between correlators. So I would like to say here that probably there is something interesting behind this 300 MeV, but we do not yet fully know what is exactly going on behind it. So let me just briefly speculate what can be. It's kind of interesting that this 300 MeV is this threshold is very close to the critical temperature in the Young-Mills theory of the confinement-deconfinement phase transition. So one possible scenario is that there can be one phase transition, confinement-deconfinement at large quark masses at this 300 MeV. Then it goes somehow goes down, then probably changes into a smooth crossover, and there might be another kind of phase transition, chiral phase transition that's much smaller temperature, of 2 times smaller than this 300 MeV. But of course, this is some kind of mere speculation. I should put a question mark here, a huge question mark. Maybe there is something else going on. Anyway, if I summarize what we have found, that our data are compatible with O4 scaling behavior up to roughly physical Pion mass, and in the temperature region between 120 MeV. We didn't go below, so that's why this is the lowest boundary, and up to 300 MeV. So if we go to this plot that I showed earlier, then physical point is somewhere around here. Of course, it's a contradiction with what was discussed, probably in contradiction with what was discussed yesterday by Jan Pawlowski about FRG results, where they observed where it is observed that their scaling region is much narrow. But it would be interesting also to understand the this discrepancy, and I'll also open this letter, put it as an open question. Okay, so, and I'm at my conclusions. So I discussed QCD phase transition, its scaling properties. It turns out that in order to discuss scaling, it's very useful to study this new quantity, psi bar psi 3, which is psi bar psi minus mass times susceptibility. The prediction, as a byproduct, we obtained the predictions of the critical temperature in the chiral limit, which is 134 MeV. The results are consistent with O4 scaling up to physical Pion mass and in the temperatures from 120 to 300 MeV. But to be honest, we cannot exclude Z2 scaling up to critical Pion masses about 100 MeV. And there is also an interesting threshold in which we observed about 300 MeV, which would be interesting to understand better. Thank you for your attention.
you. And are there any questions or from here or from the people at home?
Yeah, thank you very much for this very nice talk. I have one comment about the novel order parameter, because this is the standard order parameter which is used in Dyson-Schwinger studies for decades now. So you take the chiral condensate and you subtract exactly m times the mass derivative of the chiral condensate for precisely the same reason, to get it finite. We do it differently in the FRG because everything is finite from the onset, but this is the standard order parameter. Right? So, which makes it good because you can immediately compare to the Dyson-Schwinger results. So when they tell chiral condensate, that's what they do. Yeah. Okay. The other thing is, I mean, you mentioned this discrepancy. In my opinion, it's not a discrepancy. I would just say your scaling is not my scaling. Right? I mean, I have nothing against scaling windows, but I think you see another scaling, and I mean, you're mentioning the other works which see a large regime, which has non-perturbative physics above the phase transition. There, I'm totally with you actually. You missed actually one reference, because I know from talks of Rob Pisarski, he for a while liked to show the scale anomally times temperature squared. And that thing, at least in pure QCD, has a plateau exactly in this regime. So if you wish, up to twice the phase transition temperature. So I think there's no contradiction.
Okay, thank you. Yeah, definitely.
Other questions? Oh, please, Frischoff.
Yeah, hey, thank you for the nice talk. I actually wanted to ask about this 300 MeV threshold. I did not quite get whether this is a statement about a threshold when you increase the quark mass, or whether that is a quark mass independent statement.
This is the statement. So let's first take quark mass physical. Then even in this case, there is an indication that there is a threshold at this 300 MeV. But in my talk, I mentioned two things. The first one, which can be seen from, well, yeah, actually it can be seen from just one quark mass. So if we go back here, so the description by the O4 universality class, it works. We can fit it by take one quark mass, and it works for one quark mass up to 300 MeV, and then for physical or for higher than physical as well. And then if we combine it for several quark masses, then it's also in agreement with the observation for one quark mass.
Okay, thank you.
Okay.
We have still time for one last question, if there is something more. Okay. Let's thank the speaker again.